All right. So now we got question two, which looks to be a lab question, and it's about drag. So we have a student drops a cylinder of mass m from rest. The air exerts a drag force of magnitude F drag on the cylinder, and the student models the magnitude of the drag force as F drag equals some constant B times V squared. So we got quadratic drag. Really doesn't make a difference this time. They typically would make us separate and solve this, but not this year. They just actually make us write the differential equation, and that's it. So derive, but do not solve, differential equation that can be used to determine the speed v of the cylinder as a function of time t. So whenever we see differential equation, in mechanics at least, the main differential equation we're going to encounter is some variation of the tied and true F net equals ma. And the reason why is because even though we write it as F net equals ma, acceleration is just the derivative with respect to time of velocity. So that's what makes it a differential equation. So I'm sure that to get one of the points, you had to turn acceleration into a derivative. So actually, we're done with the right side. So now let's figure out what F net is. And well, if we think about it, we have something in free fall, except now there's a drag force too. So if it wasn't free fall, the only force we would have to manage is a downward gravitational force given by mg. So that's free fall, but this is a drag question. So we have some sort of an upward drag force, which I'll just call FD to abbreviate, and that's equal to some constant B times V squared. Do not assume they're equal. It does not tell us these things are equal, because the value of drag is going to evolve with V, which is going to evolve with time, so we can't assume anything yet. So what's F net? Well, F net is going to be, I'm choosing down to be positive because it's moving that way, although if you have all your signs flipped, I still imagine you get the point. So F net is the things helping acceleration, mg, minus the things opposing acceleration, which is bv squared, which is equal to m times dv dt. And that's it. If I were to assign point values, I would guess you get 1 point for the dv dt, and you'd get another point at least for identifying that the net force is mg minus drag. So the only unacceptable answer for the net force in this case would be any sort of addition of these two. You can subtract if you wanted to do up as positive. That would work. Okay, now we sketch the speed v as a function of time t, and that's given in this figure. Draw a vertical line on the sketch to indicate the earliest time at which F drag is equal to the magnitude of the weight. So, before we do this, we are given that the drag force is equal to the weight force. And what does that mean? Well, now if we go back to our free body diagram, we can do what we were tempted to do at the beginning and set the forces equal. So if these two things are equal, these two forces are equal, what that means is that F net is now equal to 0. And that's critical to actually getting us our answer. So we want to draw a vertical line where the drag force first equals the gravitational force. And this was not a very difficult location to guess, so the justification will be more important here. Oh, we don't want an arrow. I want just this one. So we're going to go right about here. Maybe move it over slightly. Yeah, that's about good. And we're going to label that T1. So why is this the point? Well, at this point, it's where the slope becomes horizontal. So at this point, we have dv dt equals 0. And why is that significant? Well, justify the location. Well, at T1, we have dv/dt equals 0 because the slope is horizontal, or the tangent line is horizontal, I should say. We have a slope of 0. And why is this important? Well, this implies that acceleration is equal to 0, which means that F net is equal to 0. And if F net is equal to 0, that means that the force is balanced. So F drag is equal to Fg. I can see this being either 1 or 2 points. So the line is going to be a point, and then maybe you get 1 or 2 points. So maybe you get a point for saying the slope is horizontal, and another point for saying that implies that there's no net force. Rather than dropping a cylinder from rest, the student throws the cylinder upwards. The cylinder is in the same orientation. So that's important because that's going to affect the drag constant. And they let it fall to the ground. We want to know if the maximum downward speed will be greater than or less than or equal to this Vmax that we have up here. So anytime you're asked this, instead of really trying to conceptually reason through a lot of the time, we have a formula that's going to relate these things. So we know that at terminal velocity, we know that mg is going to be equal to b times Vmax squared. That's what makes this terminal velocity special. So Vmax is going to be equal to square root of mg divided by b. So let's ask this. So the only thing that could go wrong is if the cylinder is going to hit the ground, but I believe we're led to assume that the cylinder is very far above the ground and it's not going to crash. So, well, if we look at this formula, let's see. Does throwing the cylinder upward affect m? No. Does throwing it upward affect g? Obviously not. And then b, here's where it gets kind of tricky. What is b? Well, that depends on the shape. And it says same orientation. So there's no ambiguity there. So I think we can confidently say that it's equal to, because Vmax has no dependence on initial velocity. You knew it was coming. It's a best fit line. Okay, so the student is graphing Vmax squared as a function of mass. Again, you don't need to know what the model is to get the best fit line correct, so we'll do that, and then we'll sort out why this is the thing the student graphed. So let's do that. So again, don't just play connect the data points. We actually want to attempt to draw a best fit line. So let's see. That's probably... I can do better than that. This is what happens when we do this live. I like that. Good enough. You got a problem, sue me. Okay. So here's our best fit line. Cool. Use the best fit line to calculate an experimental value for b. I know I'm going to have to take the slope, but I need to derive an equation first to figure out why I'm doing that. So, well, we only have one equation right now. They're testing different masses and seeing the Vmax that they get out of it. So, we already said earlier that at this terminal velocity point, we know that mg is equal to b times Vmax squared. Boom, our formula is done. So now we just got to identify what our variables are. So they're changing m, and they're changing Vmax squared. Well, Vmax is being changed by that. So those are our two variables. So that means we just got to rearrange this into the form y equals mx plus b. So we can solve and get Vmax squared is equal to g divided by b times m. And now we can draw ourselves our little boxes that tell us what to graph. So notice I have something equals constant times something else. So this is exactly y equals slope times x. So that's why this is the relationship that was graphed. So now we do what I call the slope two ways. So here's our slope in terms of letters. It's going to be this constant out in front. So the slope from our model in terms of letters is equal to g divided by b. So then just doing a quick swap after multiplying by b and dividing by slope, the thing we want, the drag constant, is just going to be equal to g divided by slope. So if I plug in my value for g, which is obviously 9.8 meters per second squared, and the slope, I have my answer. So let's do that. So we got to estimate the slope using the best fit line. And just so there's no ambiguity, I always recommend identifying the points. So here's a point the line goes through. So that's actually a data point. And then here's a grid square that it crosses through. So now let's just do rise over run. So slope is going to be equal to rise over run, or the difference of y and the difference in x. So let's see. This looks to be about 9.5 as my top data point, and I'll deal with the units later, because I imagine the unit might even be a point for this. And then let's see. It's just slightly below 3. I might even call that like 2.8. Or sorry, slightly below 2.5. So we'll call that 2.4, we'll say. And then the units on that is v squared. So that's meters squared seconds to the minus 2. Then divided by our run, which, let's see, our furthest data point is 0.55 kilograms. And our closest data point is 0.1 kilograms. So we do get a nasty expression for slope. And that's going to be equal to, let's see, I got to do this live because this changed from last time. Let's see, 9.5 minus 2.4 divide by 0.45, and we get 15.8. Meters squared seconds to the minus 2 kilograms to the minus 1. Lovely. Okay, so that means that B is just going to be equal to 9.8 meters times seconds to the minus 2 divided by 15.8 meters squared seconds to the minus 2 kilograms to the minus 1. And I wrote my units this way so I could easily see some canceling. So the seconds cancel, one of the meters cancel, and we're left with, let's see, I gotta get my phone out again. 9.8 divided by 15.8, 0.62. Units are gonna be meters to the minus 1, kilograms also to the minus 1. And again, this, if there's anything I did wrong on here, it is probably estimating my best fit slope by hand. Please feel free to correct me. I promise I don't take it too personally. I'm not the best estimator just by looking at the graph. We'll do a quick sanity check here. 0.55. It's going to be 9.5, yeah. Yeah, so it's all about how I drew my line, I guess. If that's good enough, we'll see. We'll find out in a couple months, I guess. Okay. And lastly, we're interested now in seeing if length of the cylinder actually affects the maximum velocity of the cylinder when we drop it. So we either could have a bunch of cylinders of the same length but different masses, or we could have a bunch of cylinders of the same mass but different lengths. Well, if we're trying to figure out how the length affects the maximum speed, that means we should measure Vmax and we should figure out how L affects it. So we are taking this set of cylinders. So how can these be graphed to figure out the relationship? Well, see if L affects Vmax. So if you get something like this, where Vmax, L, if you graph this and you get something like this, oh, maybe let's not make it that clean. Maybe like something like this. Well, that's basically no dependence right there. It's basically a horizontal line. So this would be no dependence. So that would tell you no dependence. But if you get an obvious trend, like Vmax versus L, if you get something instead that's like this, well, obviously that would be dependence. So we're really just graphing it and see if graph is constant. So check if the graph is approximately constant. So if you best fit it and the slope is like 0, well, that means there's really no relationship here. I mean, it's not necessarily a line, but you should check for obvious trends like this. Overall, very straightforward lab question. There's not a lot of theory actually required for this, which I thought was different than recent years.